Everybody, this is a guided walkthrough for the Buffer Overflow 1 challenge from the picoCTF website as part of their picoCTF 2022 event. The description of the challenge says, control the return address. Additional details will be available after launching your challenge instance. So what do they want us to do? Before we do anything, what we need to do is we need to launch the instance. So click on this blue button here. And then after a few moments, it says, now we're cooking. You can overflow the buffer and return to the flag function in the program. You can view the source here and connect to it using this over here. Okay, so we've got a couple of download links. So we're just going to hover over the word program, copy the link, then we're going to go over to our web shell. In the web shell, we're going to create a directory to work inside of. So make directory buff1, and we're going to enter that directory. Then we're going to use wget to download the first file, that link that we just copied. So we're going to see after we download it that we have the vuln binary in here. Afterwards, we can run the same wget command that we did before, but we're going to tack on a .c at the end. This is going to give us the C code source for this particular binary. Okay, and then we're going to see that we've got two files in here, vuln and vuln.c. So we're going to make the vuln binary executable by running this command, chmod +x /vuln. Then we're going to see that the binary is executable now. So before we move on, we can take a look at what kind of file this is by running the file command on it. So file vuln, it's going to let us know that this is an ELF 32-byte LSB executable. Intel 80386. It basically lets us know that this is a 32-bit binary that's in the Linux format, the ELF format. Okay, so let's go ahead and talk a little bit more about this challenge. All right, so this is picoCTF 2022 Binary Overflow 1. So this challenge is an example of a Ret2Win binary hacking challenge. So this is kind of a category of these type of binary hacking challenges. It's called Ret2Win. So according to the source code, the binary contains a win function which outputs the flag file contents when it's called. So this function here is this is the one that we want to run. Okay, so we need to find some way to run this win function over here. So the binary does not call this function normally, so we need to discover a way to call it. So if you go over to your web shell, you can take a look at the code. And the code here, it includes the win function up here. So the win function says, open up the flag.txt file and read it. But if there's no file, then it's going to tell you to create a flag.txt file in this directory with your own debugging flag. So we can create the flag by the little echo command to flag.txt. How about HackerFrogs? Like and subscribe. A little bit of blatant plugging there. There you go. Okay, so if we see this message by doing our binary hacking, then we know that we've completed the challenge. Let's go ahead and talk a little bit more about this. So what we're going to do is we're going to do some stack buffer overflow. I'll explain a little bit about the concepts behind this kind of type of vulnerability. Okay, so we're talking about stack buffer overflow. So this binary uses the unsafe gets function to save user input with a maximum buffer size of 32 bytes. So the vulnerable function over here, it defines a buff variable with a maximum size equal to buff size. and buff size is set to 32, and it runs gets. So gets is an unsafe function. It doesn't check whether or not the user input is larger than the buffer size. So you can put more than 32 bytes when you do your user input, which makes it unsafe. This means that the user input in excess of 32 bytes will result in a buffer overflow. And because buff is a regular variable, its buffer will be in the memory stack. So what is the memory stack? Let's talk about that. So the memory stack is part of the program. It's the part of program memory which stores temporary data during program execution. So we can see here that the inside of the program, it's organized into different parts. So the memory addresses over here. These are not exact memory addresses, of course. They're just meant to illustrate lower versus higher memory addresses. So in the lower memory address, you've got your program data, you've got your initialized variables, your uninitialized variables, your memory heap, and your memory stack. So what we're going to be doing in this exercise is we're going to be taking advantage of the memory stack to do stack buffer overflow. So as the memory stack grows, it progresses towards lower addresses in the program's memory. So if we were to overflow information in the stack, it would slowly start creeping up towards the lower addresses over here and overwrite these values over here. In the case of stack buffer overflow, it may be possible to overwrite memory registers. So this is another important thing we have to understand when we're talking about stack buffer overflow. It's these memory registers. So memory registers are storage locations in the CPU that hold memory addresses and data needed for program execution. So here's some example memory registers for the x86 architecture. So there's the IP memory register, the SP memory register, and the BP memory register. So these are common registers, but we only need to pay attention to one of these for this particular exercise. So there are many, many different memory registers in the x86 architecture, but the important one to pay attention to for this challenge is the IP instruction pointer register, which in this binary is called the EIP, since this binary is a 32-bit binary. So if the binary were a 64-bit binary, it would be called the RIP. So EIP is the specific name for 32-bit. For 64-bit, the specific name is RIP, but the general pointer is just referenced as the instruction pointer, or IP. So the EIP register contains the address of the next program instruction, and if we can override it with the stack buffer overflow, then we could execute instructions at any memory address we wanted to. If we can override it with the stack buffer overflow, then we could execute instructions at any memory address that we want, and this is what we want to do. So the next step we need to do is we need to find the win function address. So it's possible to get the memory address of the win function, and our goal is to put this address in the EIP memory register so it executes the win function for us and gets the flag. So let me demonstrate a couple of ways we can do this. So we've got the vuln binary over here. We can run a program called object dump, and we can get all of the headers. So all of the headers, which are the different functions and all the other objects in the binary. And we can locate the win function right over here. So the win function is listed here, and it's at this memory address. So the memory address is in hexadecimal, but it's this value over here. And what we can do is we can remember this value, and we can feed it along with our buffer overflow in order to have this win function execute. So the other way we would get this is we can examine this with the debugger. So the debugger that we like to use is called Ret2, and we'll run it on the vuln function here. On the vuln binary, rather. Anyways, we can analyze the binary with this command inside of Ret2. this will analyze the binary for us, and then we can run the function list command. So in regard to AFL is going to list all the functions, all function lists we like to say. There's a lot of different functions in here, but if we go up to the top, we can see that there's a function called win down here. So simwin, and we see it's got this memory address. So this is the same memory address that we found with the object dump file, with the object dump tool, but this is just a different way of finding it. Okay, so the next thing we need to do is this. So our goal is to use stack buffer overflow to override the EIP register with the win function's memory address. So we need to figure out how many bytes we need to send to the binary before we can read before it will enter the EIP register. So the number of bytes that we need to send to the binary to reach the EIP register is called the offset or the overflow offset value. And we can create a pattern of characters to send to the binary. So there's a special tool we can use to create a pattern of characters to feed into the user input. Okay, so let me just exit out of here for a second. So the tool that we're going to be using is another tool in the Ret2 tool set. It's called Rag2. So Rag2 will let you create a pattern that is of a certain size, and I think we're going to do 64 bytes. So the reason, okay, let me explain why we're doing 64 bytes. So we know that the buffer size for the user input is 32 bytes. So we don't know exactly how many bytes we need to send to overflow the buffer into the EIP, the instruction pointer. We're just going to guess, and we're going to send double the size of the buffer to see if we can locate our pattern inside of the EIP after the program crashes. So we're going to run rag2 64 bytes and render it in a form that we can read. Okay, so this is the pattern right here. This is what we're going to feed into the binary to crash the program. After the program has crashed, if we find any of these letters inside of the EIP register, then we can find out what the offset is. So just copy that. Then we're going to run Ret2 again. Okay. So let's analyze the binary just for fun. So inside of Ret2, we can run the program as normal by using the DC command. So DC runs the program. It asks us to enter the string. We'll paste in the string that we got from the Rag2 program, and then we will send this to the binary. Okay, so we get signal 11, and we see that the program has crashed. So when the program crashes, we can examine what's in the memory what is in the memory registers with the dr command. So dr shows us that there's a pattern. So there's a pattern in the EIP register here, and we can just copy that. Copy that directly. You're going to see that a bunch of the different memory registers have been overwritten with the stuff that we put in the user input. So EBX has our stuff in it, EBP has our stuff in it, EIP has our stuff in it. And what we can do with the Rag2 program is see what this value here that we put into the EIP equates to as far as the offset is concerned. So we see here that we've got little endian 44 characters. So little endian versus big endian. What you need to understand is that when we're feeding bytes into the memory registers or the memory addresses, they're going to be fed in from right to left instead of left to right. So normally we put stuff, we read and we write from the left-hand side of the screen to the right-hand side. But in this case, we're doing little endian order, which means we do from the right-hand side to the left-hand side. Okay, so little endian order is what we're dealing with here. So it's 44 bytes. So when the program crashes, we can see what value is in the EIP register, and then we can determine the offset. So in this case, it's going to be 44 characters. So the last thing we need to do is we need to send the payload. We can combine the offset value with the address of the win function to send the payload to the binary and get the value of the flag. Okay, so this is what we're going to do. We're just going to exit. Actually, before we do that, we're going to make note of the win function one more time. So the win function is at this address. I'm just going to copy that. I'll put it in chat just so I never forget. Okay, so what are we going to do? What we're going to do is we're going to run a Perl command. So Perl is a pretty outdated language, but we do like to use it every once in a while to craft some payloads. So let me demonstrate. So we're just going to do Perl and execute something to create a string of characters. So we can do print the A character 44 times because that's what we determined was the offset. So if we just run this command, it'll just print out 44 A's. What we're going to do is we're going to add on to this, and we're going to add on the address of the win function. So let's see, add on some bytes. So remember that the win function okay, so remember that our address for the win function is this. Unfortunately, we can't feed these hex digits directly into the binary, not in this order. Because the binary is using little endian architecture, or byte order rather, we have to do this backwards. So we need to take each one of these pairs, and we need to feed them in one digit at a time and backwards. So this would be 0xF6 followed by 0x91 followed by 0x04 and 0x08, like this. So we're just going to copy this. We're going to feed this in to our Perl command here. We're just going to put some backslashes here to separate them. Okay, and what we're going to do, if we just run this command here, wait, hold on, let me take a look at my, okay, this isn't the format. Just a second. So the format is wrong. We just need to do, we need to do it like this. Okay. So the thing about this is that, you'd think that it would be okay if we could just type all this stuff out, but most of these characters that we're sending, they're not ASCII, they're not characters that we can type out on a keyboard. So we need to specify that these are hexadecimal bytes by sending a command like this. So we're just going to run this command here. We're going to pipe it into the vuln binary. Okay, so we feed this command into the vuln binary, and then we get the contents of the flag. HackerFrogs, like and subscribe. Okay, so we know that this is the proper payload here. So what we're going to do is we're just going to feed this to the binary running on the server, and I just need to start that back up again. Okay, so this is the netcat command here. So we're just going to run this command. We're going to feed it into netcat like this. So Perl, and then the print command, and then the netcat command with the pipe in the middle. Please enter your string. Oh, you know what? I think I screwed up. So there's one more thing we need to send in the Perl command. We need to send the null byte to terminate the string. So we're just going to go over here and we're going to add a null byte to it. So x00, please enter your string. Hold on. What is the hex for the null byte again? Or wait. What is the byte for the carriage return or the new line? So new line hex code. Is it 0A? It's 0A, okay. All right, so what are we doing? So on the end of this, we're just going to tack on a 0A. And okay, that was able to send the new line along with the payload, and then we get the flag. So picoCTF addresses are easy, and then this. So the reason we needed to do that is because the binary needed us to send a new line along with the payload. So that's what we did. All right, so we can go back to the picoCTF page, paste in the flag, and then submit the flag. All right, everybody, that was a guided walkthrough for the buffer overflow. Oh, this was a buffer overflow 1. The buffer overflow 1 challenge from picoCTF, the picoCTF website, from the picoCTF 2022 event. If you enjoyed this guided walkthrough, please click on the like and subscribe buttons on the video and leave a comment underneath the video. But until next time, HackerFrogs out.
Hey there, HackerFrogs! Are you enjoying this workshop? Learning new concepts and skills? If so, there's a way you can support the channel, and it's totally free. Just click on the subscribe button below the video. Also, click on the like button. And if you have questions or comments on this workshop, please leave them below the video. Thanks for listening. And now, back to our scheduled programming.